Everyone. So today we're going to be working on some applications. So we're on page 32. We're going to be on 2.5 and 2.6. We're going to finish out this lesson. So this is day 4 of a lesson, such a rad lesson. All right. So we have this pendulum. And if you remember, if you've seen a pendulum before, maybe most of you guys will have seen it. There is one. So there is a pendulum in UW. And so this is a picture of UW at night. It's really nice. This is the physics building. And here is, you see this, like, you can't really see with that color, I suppose. If you see this big glass ceiling type roof type thing. Anyways, this is where the pendulum is, right? And so if you can imagine in your brain, so that's where the pendulum would be, and it swings like back and forth. And in here, you can actually see some stairs. I don't know if you can see it, but there is some stairs back here like that kind of go up like that. And this is what it looks at the inside. And there was a video of this, but if you want to just look up Foucault pendulum, University of Washington, it's like a really short clip of that. It's really nice. It just goes back and forth, right? It's kind of cool. This website right here is actually, it has more information about pendulums. Quite interesting. Too bad you can't just click on that, right? But here we go. So that's what a pendulum, so basically it's one of these things that just kind of like, there's like usually a ball at the end, usually a heavy ball, and it just goes back and forth, right? This is actually how they proved that the Earth rotated instead of like not rotating, right? This is how they proved it. If you're curious about that, well, you could read about it. Okay, so this is what they calculated. So they found they figured out a formula. So T equals 2 pi square root of L over G, where T is the time in seconds. Okay, so we're measuring in seconds, and L is the length of the pendulum in meters. So that's how long this guy is right here. And G is the acceleration due to gravity in meters per second squared. If you did not know, gravity is measured in seconds squareds. You can do that with units. And if you are not in physics, you're like, well, I don't know how much that is. It's actually highlighted right. I highlighted right here. It is 9.8 meters per second squared. Okay, and somebody had asked in a class, well, is it ever not 9.8? Is it always 9.8? If we're talking about meters per second squared, we don't change the units, then yes, it's always 9.8. How do we change that? Go to the moon. They have different gravitational pull there, right? It'll be smaller than that. And we use technology to graph this. So we used Desmos. Let me go get Desmos. And so if you bring up your Desmos calculator on your phone or on your computer, I would practice this. This is a good thing to practice. So you go to, and then where, again, you do not put in the T of L. You just put in the right-hand part, just the formula part. Okay, so it's going to be 2 pi, and notice pi is right down here. 2 pi, and then we're going to go square root. It already knows that it's going to be multiplying. So what are we square rooting? Notice we don't have L, so we're going to put in X. X is it takes the place of L, divided by 9.8. So 9.8. There we go. And if you can see right here, yep, we have something that looks like a square root, right? Which we should, because it's a square root. There's a square root in there, right? So notice it starts at 0, 0, just like that. And what I just did was I just kind of, at these points, I kind of found out where 2 was. Oh yeah, 2 is, the Y is 2.838. So it's about 2.8-ish. So that's why we plotted them right here. So I just went every 2, you can go every 1. And then I kind of skipped forward to 14 so that, because I didn't want to have to do all of them. I know it's pretty predictable. So once you get this curve going, there's not going to be all of a sudden like a spike in there or anything like that. So I just went, once I got the basic shape of it, then I'm like, okay, let's go to 14. All right, so make sure you do that as well. Practice. Try to see, okay, if you're like, I don't know how you got those points. Look, try to find it. So put your mouse over. You may need to click on it. And then you're like, okay, there's where X is equal to 4. Oh, Y is 4.014. So it's slightly above 4. If you notice right here, I made it slightly above the 4. All right, and so that's how that's going to go. And there's our graph. And number 3, which is on the next page, is talking about the domain and range. So I just wrote it here. And notice domain is going to be from 0 all the way to positive infinity. And our range is also from 0, that's the lowest it could go, to positive infinity. So now in real life though, I mean, so domain is talking about the length of the pendulum. Could we go to infinity? Could it be infinitely long? Well, no, you wouldn't be able to find the end of it, right? So yeah, so probably we're thinking maybe it would be 100 meters, maybe it's 150 meters, but it wouldn't be like 1,000. Well, if you really wanted to try, but 1,000 meters is quite large, right? And you'd have to like put that up in the air. So that would be interesting. If you ever be an architect, and that would be like if you have a building, right? If you build a building, and on the very top floor you start this pendulum, right? And then there's going to be like a hole, where everybody can see. You know how you can see like with a fence, or what, a ladder fence, railing and stuff like that, and then like there will be a railing on each floor, right? And then you could see this thing like swinging, going back and forth. That would be interesting. Too bad I'm not an architect. But that would be an interesting one, where you could have one of these pendulums up like that. Okay, so for anybody who want to be an architect, that would be a good challenge. So yeah, so it wouldn't be that long. And so it does not go to infinity in reality. Same thing with the range. Well, how long is one swing? And when we say swing, we mean one time going forward and one time going back. So like that's one full swing, right? It's not just one way. And so the range, so how long does it take for that one swing to happen? It's not going to be infinitely long, right? That would be weird, right? It goes and it just never goes, but you just wait for it, it just never goes back, right? So it's, we're probably thinking maybe 15 seconds, 20 seconds, right? Like the longer it's going to be, the longer it would take for it to go and swing from side to side, right? Because the radius is longer. It's just a circle. All right, X and Y intercepts are just going to be at 0. And so what does that mean? So when the length of the pendulum is 0, the time that it takes to swing is 0. Like it's kind of, excuse me, it's like kind of a moot point. It doesn't even make any sense. Like you would not ask that, right? So I kind of want to say that shouldn't even equal 0 at this point, right? Because then it's like, why ask that question? But that's what the domain and range would be in theory, right? And then so if we look at this one, number 4 right here, how long does it take for one complete swing when the length of the pendulum is 0.5 meters? So this is our equation right here. So this 0.5 meters, that is the length of the pendulum, right? So we're going to plug that in for L. So notice right here, we just put in 0.5 for L, put 0.5 here. So this is just saying what would be the time if the length is equal to 0.5, right? That's what it's asking. And so you're going to put this in your calculator. For those of you guys who have this kind of calculator, this is how you would do it, or something similar to this. So we're going to go 2 pi. So pi is right over here above the caret. So we got 2 pi. You don't have to put times because TIs know that just means times. And then we're going to go square root. So second x squared. So above that is that square root right there. And then you got 0.5 divided by 9.8. Okay, and notice that's all under the square root, which is what you want. If your calculator doesn't put it all under the square root, then you're going to have to use parentheses around that. So I would, again, use your own calculator, the one that you would use for a test, and practice that, because you don't want the calculator to be the reason why you got it wrong. It's bad days. All right, and so you get 1.419. We'll just round it to 1.14. Or here we round it to 1.42. So that would take 1.42 seconds to go forward, to go back. Okay, so I mean it's pretty short. It's only half a meter, so it shouldn't take too long, like 1.5 seconds, right? So this one we did in one of the periods, but we're not going to do this one here. This one would be interesting, and if you do actually make a design, send it to me. I would love to know, and I would love to see your design for those people who like to design things. But read them; they do have some constrictions in there. Yes. So here is the one. We couldn't go over this in one of my classes, but so many museums display what is known as a Foucault pendulum, which is exactly the UW pendulum. That is a Foucault pendulum. As a Foucault pendulum swings back and forth throughout the day, the Earth's rotation causes it to appear to move in a circular direction. So literally the pendulum is actually not moving, is not shifting, like it's not shifting. It's like it just literally just stays moving like this, right? But what's moving is the earth. The earth is rotating. So this is actually the proof that the earth was rotating before we could even go up into the sky and like see, oh yeah, the earth is rotating. It's not that the clouds are just, the earth is actually rotating, right? So like, how would you know that if you didn't go up in space? So this is that proof, because it should just stay in place. But if you've ever seen one of these, it actually does move. So it does look like it's moving, but it's actually not moving. The earth is moving, which it does, but yeah. So, and it has to do with one of Newton's laws. If you could figure that out, yeah, let me know. It was one of them. Okay. So, and so we're saying that the earth, if the pendulum takes 1 day to come back to its initial position, right? And so it comes back to, it looks like where it started, right? About how many full pendulum swings occur each day. And also another little tidbit I did not know, and I learned this to get ready for this, is if you're in the poles, like the North Pole and South Pole, it will do one full rotation in 24 hours. But if you're in like the Northern Hemisphere and the Southern Hemisphere, apparently one of them goes clockwise and the other one goes counterclockwise. What? I thought that was cool. And then at the equator, it doesn't even do a full rotation, which was weird. And so I kind of want to go to like Hawaii, which is close to the equator, and see if that's really true. Just to go there and find out that, right? But yeah, I thought that was very interesting. So it makes me wonder, why does it go clockwise and why does it go counterclockwise? Makes me wonder about that. Makes me want to build one here. But look it up and see. And so so we found a mistake. There was a mistake in the book. And so in the book, it says this. So this was the, you can't see, it's in the teacher edition of the book. And so this is what they had, this was their work. And tell me why this is wrong. So they plugged in 200 because if you notice right here, the wire, this is 200 feet long. They obviously did not draw the whole thing because that would take a lot of space. But why is this incorrect? Because would you not put it in here? Because that's the length of the pendulum. And so some people noticed and it was like, well, this is in feet and it's supposed to be in meters. I'm like, you're absolutely right. You can't just put 200 feet. What's in different units, right? In this equation where it's talking about meters per second, right? You can't do that, or just meters. And if you look back here, I'm gonna go a little bit further back. Notice, remember, it said the length of the pendulum in meters. That's important. So if you're in physics class and you're using the wrong units, you're going to get the wrong answer because that equation or that formula is not for those units. So if we wanted to do it in feet, then we should be using other numbers, right? Because even for the gravity, that's 9.8 meters per second squared. And we would need it in feet per second squared, which is a different number, obviously, because that rate would be different. Okay. It's just equivalent, just different numbers. All right, so here we go. This one, we already did that one. So here we go. So over here on the right-hand side, I kind of showed you how, not kind of, I did show you how to convert it. If you don't have Siri, or if you want to know what Siri is thinking and how Siri does it, this is what they're doing. This is how you program it, right? So you can not only multiply units, but you could also, that's how we get the second squared. You can also cancel them out. So you can divide them out, right? So I'm going to multiply by 1. And if I multiply by 1, am I changing the way it looks? No, am I changing the value? No, I just changed the way it looks. But I'm not changing the value, right? So normally if I said 12 over 1, and if I'm multiplying 200 by 12, I'm like, no, I'm multiplying not by 1, by 12. But if you look at the units, it's 12 inches over 1 foot, right? If it's 12 inches over 1 foot, that's 1, right? Because 12 inches equals 1 foot, right? And so I put the foot on the bottom and then the feet on top. And some of you guys may be wondering, do I really need to know this? Not for the test, but it's good to know, right? So, but if you're like, Miss Lee, I can't even, like, this is too much. You could fast forward me, I won't mind. But I use this actually quite often. And to convert stuff. And there is one thing that you do need to know, and you didn't just memorize it, so that you need to know that 1 inch is equal to 2.54 centimeters. Some reason in 8th grade when I learned it, it just stuck. Like I never forgot it for some strange reason. So it is 2.54 centimeters for 1 inch. That's how you convert from standard to metric measurements. And then once you have that, there are 100 centimeters in 1 meter. So when we multiply straight across, we get 200 times 12 times 2.54. And then you just have to divide that by 100. And I will bring up my calculator and then we'll try this one more time. So again, we're going to go 200 times 12 because we have 200. If you think of it logically, we have 200 feet. And in those 200 feet, each of those feet have 12 inches, right? So it's times 12. And then we're going to multiply it because each of those inches have 2.54 centimeters. So 2.54, right? And then, but we don't want it in centimeters. We want them in meters. So how many, so we get the answer of this. And then how many meters or how many centimeters are there in a meter? Now think of centi. I think of either centimeter, century or cents, right? So how many years in a century? How many cents are there in a dollar, right? Both of them, 100, right? So that's how you figure that out. So we're going to divide this by 100. And that would equal 60.96. And so now we have it in meters. So yay, happy days. So this is 60.96 meters, which is going to be, so, oh, there it is right here. So this is incorrect, wrong units. And so we're going to put in 60.96 instead, because now we have it in meters. And that's going to be, once we calculate that out, that's going to give you 15.67. Again, if you did not do that on your calculator, try it. See if you can get that answer. It's a good way to practice it. So it literally takes about 15 and a half seconds to go back and forth. This is a very slow pendulum, right? Very slow, because it's really big. 200, like 60 meters is quite large, right? It's, I think like half a football field, right? I almost want to do this calculations. How long is that? All right. So, but that's not the question. It wants to know how many full swings can we get. So we know that one full swing is about 15.7 seconds, right? So how many of those 15.7 seconds do we have in a day? Well, how many seconds do we have in a day is the question, right? And so what you can do is you take the 24 hours, you know that because there's 24 hours in a day, right? That's what we're getting, 24 hours. 24 hours, and then we want to convert that to seconds, right? So we know that for every hour, there's 60 minutes, right? So hour goes on the bottom because we want to cancel out the hours. And then we know that for every 60 minutes, there are 60 seconds. So we're going to have to multiply that. So all we have left is just seconds. So it's going to be 24 times 60 times 60, which is going to be 86,400 seconds. So if you really think about it, we only have 86,400 seconds every day. What do you do with that time? How much of it do you waste? And some of it you should be sleeping. But yeah, it kind of makes me want to be more productive, right? All right. So so now we're going to just take this, and what we did is we're just going to divide it. So we're up here now. I don't know why we're all the way up here, but I kind of just did that. So we're up here. So we're going to 86,400 divided by 15.67. How many of those to go in there? And that's going to tell us how many swings that is, right? So we're at about 5,513 and some change swings. So how many full swings? 5,513. That's how many swings. So I should write that down. So 5,513 swings. That's a lot of swings for one day. Poor pendulum is probably tired by now. All right. So that's how that goes. So this was the whole thing, application on pendulums. And we have another application is 2.6, which is centrifugal force. A lot of physics going on here. So if you have not taken physics, get ready, it's coming. All right, and so if you've ever ridden on one of these, for me, I know it as the Gravitron. I know they have one in Wild Waves. Somebody I think called it like Disco Top or something to that effect. I don't remember. But yeah, this is like an indoor one. So if you notice right here, oh, I did a lot of drawings on here. So erase that. So you can see it here. So if you look at this, right, do you notice how they're like on the wall, but they're like literally sticking to the wall? Nobody's like going there. None of them have their feet on the ground, right? Why is that? Because this thing is spinning fast enough where are, yeah, it's fast enough that that force is keeping you against the wall. And if you've ever been in it, I've tried to like lift up my hand and it's so hard. And you're like, wait a minute, what? How hard is it to like touch my nose? But you're just like, it's really hard. And somebody else likened it to, like when you take a bucket of water and you swing it around, but you have to swing it out fast enough, swing it around fast enough so that the water sticks to the bottom of the bucket, right? Because if you don't, you're too slow, what happens, right? If you're too slow, you get wet. Sad days for you. So there is that minimum speed, right? What is that minimum speed that you need in order to, have people stick to the wall and not like have people like flung around? Because could you imagine if you didn't stick to the wall here, you'd be like, whoop. Yeah, you'd be going on. Yeah, that would be sad days. So yeah, you would be going this way. So that's why you're like, before we lift up, we've got to make sure we're going fast enough, right? And so you need to reach that minimum speed. And so this highlighted a formula here, that's how you figure it out. So it is based on the radius of this contraption here, and it'll give us the speed. So if you notice right here, the radius, let me just kind of erase all these. Let's go with, this is the radius. So from the center out here. So that's our radius, right? Remember, diameters are like all the way across from end to end. So radius from the center to the end. Okay, so see, who knew you still needed to remember geometry? It's all related. Okay, so let's see here. So an amusement park designed a rotor ride, see, Gravitron, with a radius of 2 meters, 2 meters. At what speed did it need to spin? Or at what speed does it need to spin? I can't talk today. All right, so again, this is our radius, our 2 meters, right? Because it says radius of 2 meters. And so we're going to plug that in for r. So s of 2 is equal to 4.95 square root of 2, right? You're going to put this into your calculator and out pops the answer because, we don't have to figure out square roots of 2 by ourselves. So 4.95, just like this, square root of 2. So make sure you're using the square root and not the square button. Some people get confused. All right, make sure that's not. You notice it's like literally it's like 7, and some very, very little change, but we're gonna just round that to 7, right? We don't have to be that accurate, right? So it's going 7 meters per second. Okay, 7 meters per second, and then doing the exact same thing for 4. So practice 4. See if you get 9.9 seconds. It's a good way to practice that. Again, pause if you need. I'm just going to keep on going. You pause me whenever you want me to pause, right? I will rewind too, right? This is like all-purpose kind of thing, right? So number 3, the designers at a park have a motor that could spin a rotor ride at 6 meters per second. Now we know the speed. Now the question is, how long is the radius, right? How long is that radius for that ride? So literally we put in the 6 for the S of R, right? Remember S of R, they come together. They're not separate. So this is like literally like your Y, right? So that's why we're just replacing the whole 6 and we're not doing S of 4, like S of 6. We're not doing that because the S stands for the speed at 4 seconds or 4 meters for the radius, right? So the 6 equals to 4.95 square root of R. So first thing we would do is divide out the 4.95, right? And then you would get this. And how do you get rid of the square root? With a square, right? So we're going to square both sides. And you should get the answer of 1.469. If you do not, I would check your parentheses, make sure you're squaring both the 6 and the 4.95. That's another place that people can get messed up on. Someone had said in the chat before, well, can we just square both sides? And I was like, well, yes, you can, but this is what it would look like. And so notice right here, you would square both sides, but when you do that, you need to also square the 4.95 because it's there, right? So that would be 24.5025 times R, right? So notice the R, the square and the square root cancel out. So you're just left with the R. Then you would just divide both sides by 24.5025. And then you, again, see how you get the same answer? So you can do it that way. It's not conventional, but you got to make sure that your math is right because a lot of people will do that, but not square the 4.95. And that's where you go wrong. That's where you're like, ooh, it's wrong. Okay. And that would be really important if you're an engineer, right? Because we don't want to make those kind of errors. This is why buildings fall and bridges fall and things like that, right? Because of those kind of the little errors. And you're like, oh, it's just That's just the one little square there, right? That's a big difference. All right, so number 4. Designers estimate that they must allow 60 centimeters of space along the wall for each person on the ride. So notice where am I? Okay, so here, do you see this guy? 60 centimeters. So it's about 0.6 meters for each one of those guys, right? So to make it safe and nobody's running into each other, nobody's like bumping into, we don't want that, right? So, but then they also want a minimum, they don't want to give them too much space because then they can't get enough people in there. They want to make more money, right? So you got to have that good balance. So there's like 0.6 is good. And so the first thing we need to do is, okay, so here, this is like your overview, like your bird's eye view of it. And here's their 2 meters. Where am I getting the 2 meters? This says from question 1. So if you remember question 1, what does it say? 2 meters, okay? We would also do this for 4 meters, okay? Same idea. So what is the maximum number of people? Well, first, so this is gonna be like 0.6, this is 0.6. So how many 0.6s can we put on there? We're like, well, what do we need? We're like, oh yeah, the circumference. So if you remember way back in the day, circumference is 2 pi r, right? 2 pi r, we know the r is 2. So we're gonna place that in with 2. And then 2 times 2 is just 4. So it's 4 pi. Well, what's 4 pi? Let's do it on your calculator, right? You could use 3.14159. I would go up to there, just to be more exact. 3.14 is usually not as exact. I hear that engineers use 3.14159. So that's why I memorized up until there, because you don't usually need to be that much more accurate than that. Up to you. Be an engineer and then tell me. Let me know if it's actually something else, if you go further. And then we got this circumference to be 12.566. So about 12 and a half, a little bit over 12 and a half meters all the way around. Okay, so how many people go in there? So this is where we would have to divide that number by 0.6, right, to see how many people we can have. And so so we get the answer 20.94-ish, right? And I was like, well, and so a lot of people told me, well, it's 20 people. I'm like, well, don't we round it up to 21, right? Because it's closer to 21 than it is to 20. And so people told me that you can't just do that because you don't have enough space to put 21 people. You have almost enough space, but not enough. So I'm like, fine, I guess. So 20 people it is. So we can only fit 20 people in there. We'll have a little bit of leftover. So maybe that'll be just spaces in between. I don't know. But yeah, so only 20, the max number of people is 20 people. That's it. Okay. Oh, and another thing, the difference here, just remember that pi is spelled P-I, and this kind of pie is P-I-E. Well, this is supposed to be like apple pie. Okay, that's the edible pie. And maybe I should make it like more 3D, like where you can see the bottom and all that kind of stuff. I don't know. Anyways, so we did not talk about these ones. Well, I would read them and see them, check them out. If you have questions on them, it's interesting. These are interesting questions. And this one is actually where you get to design your own rotor ride that fits these dimensions. So if you like to practice like your design because you want to be an architect or you want to be some kind of engineer, this would be a good one to kind of problem solve that, right? So you have to fit it within certain like criteria, right? So email me, let me know on that. I would love to see it, right? I'll see you later. Bye.